Hi guys, let's continue our look at aromaticity. And let's pick up here with comparing benzene to cyclobutadiene. Benzene is an aromatic compound which has an unusual stability due to cyclic conjugation. Cyclobutadiene has an unusual instability due to the full cyclic conjugation that we see. Both of these molecules have full cyclic conjugation. So why the difference in their stability? We have to go to molecular orbital theory. Okay? And we will begin with molecular orbital diagram of butadiene, or 1,3-butadiene. It is not a cyclic system, but we will begin here. Now, in the other handout, we do have a page that shows the keys to drawing MO diagrams for cyclic conjugated systems. Okay, like a cheat sheet. Some of these things we will point out even here when we do butadiene. So keep that sheet handy. We'll also look at this picture there. Okay. I could begin with the theory discussion, or we can begin with just showing the MO diagram. When I say MO diagram, I'm talking about an energy diagram of the molecular orbital levels. Okay? Now, we should first take stock of what we have here. We have 4 p orbitals, and we have 4 pi electrons. Now, whenever we do an MO diagram here, we're only going to be looking at the pi system. Okay, and this is what we have with regards to the pi system. Now we will say that if you have 4 p orbitals, we're going to get 4 molecular orbitals. Now, p orbitals, these are the atomic p orbitals. All right, of course we have the molecule, and each carbon has a p orbital. Each atom there has an atomic p orbital, 1 electron, and those two overlapping to make pi bond that we see, 1 electron here, 1 electron here, overlapping to make pi bond that we see here. Of course, there's also overlap between p orbital 2 and 3, and so we have delocalized bonding through here. We have extended conjugation throughout the 4 p orbitals. Okay. But this is a valence bonding view, and the orbitals, even though they're hybridized, they remain as atomic orbitals. Whenever we go to molecular orbital theory, we combine these atomic orbitals and we create a new orbital that is spread over the entire molecule, and we call that a molecular orbital. And once we get to molecular orbitals, the atomic p orbitals no longer exist. Okay, this is the theory. All right. Now, if you have 4 p orbitals, 4 atomic p orbitals, you're going to get 4 molecular orbitals, because in this theory we combine these in 4 different ways to make 4 molecular orbitals. If we had 6 of these, we would make 6 molecular orbitals. Okay. Let's first show the energy of these orbitals, and then let's sort of go back and draw them. The energy is going to be, okay, we can show energy. You're going to have 1, 2, 3, 4. 4 molecular orbitals. This is the energy levels. All right. Now there's going to be a midline that comes through here. Energy midline. Those below the midline are typically always going to be bonding molecular orbitals. Okay, let's just say bonding MO, bonding MO. Those above are going to be anti-bonding molecular orbital. All right. Now, the midline is actually where the original 4 atomic p orbitals would sit. Okay? But when we make molecular orbitals, we're going to get energy below, or some lower energy orbitals, and then we'll get correspondingly higher energy molecular orbitals. And so the midline cuts symmetrically through here in terms of energy. We will develop this discussion as we move along. Okay? Now this is just kind of scratch writing. Okay, right here is our MO energy level diagram. Okay, well, what do these molecular orbitals look like? Let's take some time to think about that. Now, we're going to combine these 4. Now I'll draw them in. As we move along, I won't draw the p orbitals in. I'll just use a plus and minus to denote the phase. We'll do that here. But let's ask the question, what's the best way that all 4 of these could combine? And the answer is for them to combine all in phase. And I'll denote that phase with a positive like this. Okay? And so these are all combining in phase. We can call that a bonding interaction. We can also call it constructive overlap. All right. And that becomes our first MO, okay? Or 1 MO. We have to get in our minds that this is no longer 4 p orbitals. It is now, they've all now combined to create 1 molecular orbital. Now, we can move up. There's another way that these can combine. And this will be higher in energy, and that's why I'm kind of going up. Okay, I'll draw the p orbitals again, but then I'm not going to draw them anymore because it just takes too much time. We could combine these 2 in phase, that is bonding interaction or constructive overlap, and these 2 in phase but opposite that, and we could end up with something like this, and this would be also a bonding interaction there and here in phase, okay? But between these 2, we do not have any bonding interaction. We would call this destructive overlap. Okay? We could possibly call this, I think it's appropriate to call this an anti-bonding interaction. Let's just call it constructive destructive. But what we have here is a node. Okay? A node is a plane where it splits through the molecular orbital where there is no electron density. Okay? So here's our second MO, and we can note that it has 1 node. And by the way, if we go back down here, this one has 0 nodes because there's no plane through this MO where there's no electron density. Now, we will see that as you go up in energy, you get 1 more node. So the next one will have, guess what, 2 nodes. All right? And that can actually help you determine what the MO will look like. Now the nodes are going to be symmetrical. We can put 1 here and here. I'll do the p orbitals again. And in this case, they interact in this manner. Well, if this says positive phase or 1 phase, and we see that there's a node here, that means there's no overlap here. No electron density between these two, so that one's going to be negative. That leads to this being a node. But apparently we do have overlap here because we didn't see a node, so we want this one to be negative, and those two have the same phase. And then this one would be positive. And then you see there would be a node there. So this is our third MO, and this has two nodes. Now, we can also say this. The midline is going to be here. Remember? Two below, two above. All right? Now, we call these bonding molecular orbitals below and antibonding above. If we look at the interactions here, we have a bonding interaction, a bonding interaction, and a bonding interaction. Okay? That's 3 bonding net. So that is a bonding molecular orbital. This one had a bonding interaction, but here we had and here I would call this, okay, a bonding interaction. We call this an anti-bonding interaction. Indeed, we should do that. And what's the net here? Well, one anti-bonding cancels one bonding. And we're left with one bonding net. So net-wise, it's still a bonding molecular orbital. But it's not as good of bonding as this orbital would provide. That's why this orbital is lower in energy. All right. Now, if we go above the midline, we expect these to be anti-bonding, yeah? We said that right here. And indeed, if we look at the different interactions that led to this molecular orbital, we have anti-bonding, bonding, anti-bonding. One anti-bonding cancels a bonding. What are we left with? One anti-bonding net. And so we call that an anti-bonding molecular orbital. Now the fourth one, instead of drawing the p orbitals, can I just use the sign? Now we also have, this is going to be our fourth, we're also going to have 3 nodes. As you go up, you increase the number of nodes. 3 nodes would be here, here, and here. Okay? Now if this is plus, okay, really, I'm not going to draw in the p orbital, but it'd be just like if that was plus. And this would be minus, okay, because there's a node between here, but there's a node between these, so we go back to plus. Opposite phase interaction here. And then we want opposite phase interaction here. And so we see that if these 4 combine in this manner, really none of them would be constructively overlapping. And there would be nodes between all of them, and you would get 3 nodes. And the net interaction here would be anti-bonding, anti-bonding, and anti-bonding. That would equal 3 anti-bonding net. So we see it's an anti-bonding molecular orbital, just like this one, but it's worse in terms of energy because it's got more anti-bonding interactions. So this here is 4 molecular orbitals. Okay? Now, what do we know about an orbital? How many electrons can sit in an orbital? 2. We're going to put 2 electrons in this orbital, and the electrons will be spread out all through this orbital, this MO. Now we can come back over here and show that like a ground state configuration, but we're going to call this a molecular orbital diagram of the pi system of butadiene. Now when you have your energy levels, you can put your electrons in using off-ball principle, Hund's rule, Pauli exclusion principle, 1 electron here. Okay, then the next one, opposite spin, right? Then off-ball principle, we go to the next level, 1 here. then we come one here. And there's our 4 pi electrons. And there is an MO diagram for butadiene. What do we see? I see all electrons paired. Okay. All electrons are in bonding MOs. And this is the 2 main things. This number 1 being the most important. Okay? The 2 antibonding molecular orbitals are sitting empty at ground state, but this theory, and by the way, this is very introductory look at the theory, but this theory allows you to then consider excitation of an electron from one orbital to a higher energy orbital, such as in UV vis. By the way, this orbital would be called the HOMO. Hopefully you've heard some of these terms before. Highest occupied molecular orbital. And this would be called the LUMO. The lowest unoccupied molecular orbital. And you often hear of an electron being excited from the HOMO to the LUMO. All right. There's probably more we can say, but let's move to doing an MO diagram for benzene. Now with benzene, we need to start with taking stock of what we have. We have 6 p orbitals, and we have 6 pi electrons. All right, you should see that from just the valence bonding that we see in the structure. Since we have 6 p orbitals, we're going to get 6 MOs, 6 molecular orbitals. Now, the energy levels are going to look like this. First off, you will have one at the bottom. The one at the bottom, there's only going to be one at the bottom because there's only one way to combine them with all of them overlapping. So we're always going to have one at the bottom. But a difference with cyclic compounds is as we go up, we will have 2 at the same energy level. All right, and these are going to be called degenerate. Okay, this is our energy. Degenerate molecular orbitals have the same energy. That's 3. We're going to have 3 below the midline. And we're going to have 3 above. 3 above, we'll have 2. And then we'll have 1 at the top. Now, as we go forward and have different numbers of MOs, you will always start with 1 at the bottom, because there can only be one way for them to all interact in phase, and that's going to be your best molecular orbital. And with the cyclic ones, we then have 2, 2, till you run out. If you have an even number, like 6, you'll end up with 1 at the top. If we have an odd number, like 7, it'll be 1, 2, 2, 2. There'll be 2 at the top. We will see that later. So these are the energy levels. These are going to be bonding molecular orbitals below the midline. These are going to be anti-bonding. This is going to have 0 nodes because there's overlap all the way around. Constructive overlap all the way around the ring, leading to this MO. All right? But as we go up, this will have 1 node, this will have 2 nodes, and this will have 3 nodes. Yeah? Okay. Let's draw these, and then we'll come back and we'll fill in our electrons. Okay. I'm not going to draw the p orbitals. We're just going to do the phase. And if we did have p orbitals here, they could interact all in phase, and I'll show that like this. Okay? And so there's interaction between every one. All right? Just to recap, the way I'm doing this, I'm not showing the p orbitals. If I did, I would do it like this. And I'd say plus, 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 plus. And I would say, hey, since it's the same phase, they're all interacting. Okay? So, when I do it like this, you just have to see what I'm talking about. And thus, there's no node. I can't draw a plane through here indicating where there's no overlap. There's overlap all the way around. All right? So there we go. And that's the lowest energy one. Now, there's 2 above. I'll draw a line here. I'll draw them on top of the line. Now we know these have 1 node, and to get 1 node there's actually 2 different ways to get 1 node. I can come right through here, and I could put these top 3 in phase, and then we see that we need no constructive overlap here, so that would be minus, minus, minus. By the way, we can also go back down here and do this. We have a bonding interaction, bonding, 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 and that's 6 bonding net. You see that? Here we have bonding, bonding, anti-bonding, bonding, bonding, anti-bonding. And the net is 2 anti-bondings cancel 2 bondings, 2 bonding net. With 1 node, that is, there's no electron density coming right through here. We have electron density above and below. So there's a node in the molecular orbital. There's another way to get this same outcome here with 2 bonding net, and that is if the node went right through here and it actually went through 2 nuclei. And if this was plus plus and we made this minus minus, we would see that we have a bonding interaction and a bonding interaction, and that's it. 2 bonding net. Because here, these are too far away to interact, and there's actually no electron density on the nucleus. It's kind of weird, yeah? Very weird. Again, this is an introductory review. Some advanced questions may come up. But it does lead to 2 bonding net, and we see the 1 node. We will look at the pictures again, okay, over here. Once we draw all 6. Got a midline through here. All right. We can come up and draw the next 2. This will have 2 nodes. And let's see if we can identify 2 nodes. We can come through here and here. That's not coming through any nuclei. If we make this positive, negative, negative, positive, negative, negative. We have a bonding interaction. We have an anti-bonding interaction. Anti-bonding, bonding, anti-bonding, anti-bonding. And what's the net? 2 anti-bonding cancel 2 bonding. We're left with 2 anti-bonding net. So this is an anti-bonding molecular orbital with 2 nodes. The energy will thus be higher than the bonding molecular orbitals. And it's also above the midline, so we expect it to be an anti-bonding molecular orbital. The reason it's above the midline is because our midline is going to cut symmetrically through. You're going to have a certain amount of energy below and that same amount of energy above. Another way to get 2 nodes is to come right through here and right through here. And this is going to be an anti-bonding interaction. And hold on, let's make this plus, minus, plus, minus. Because this node is coming right through the atom nucleus here. And we have 2 anti-bonding interaction net. That means it's going to be equal in energy to the other one that's 2 anti-bonding net. So 2 molecular orbitals, these are degenerate. They're at this energy level. Then we have the last one. It's going to be a single one at the top. And it will look like, first off, how many nodes? 3 nodes. Those are going to be, I believe, boom, boom, and boom. And if this is plus, that's minus, plus, minus, plus, minus. And this is actually where none of the 6 overlap in a constructive manner. All 6 are overlapping in a destructive manner, leading to 6 anti-bonding net. Because if you look, every interaction is anti-bonding. All 6 interactions are anti-bonding. I won't take time to go all the way around. Highest in energy. Here are your 6 MOs. In one of the other handout, it shows a view of these, a top-down view, with the dark being electron density. You see this one here, where it has constructive overlap all the way around. You see electron density can exist all the way around the molecule. So this is the best MO. Then these 2 MOs, they each have 1 node. Do you see the plane through here where there's no electron density, called a node? And we had bonding interactions above and then below. Yeah? And this one over here, here the node actually cut right through 2 atoms. Okay? So you can look at all 6. Here's the worst. Okay, the worst is where there was no constructive overlap anywhere around. All right, 3 nodes. So this is 6 molecular orbitals. A lot of math here in this theory. By the way, this came out of the Wade textbook, which is the textbook I learned out of as an undergraduate. Wade being the author's last name. Okay, so they're the actual MOs that we tried to draw there. Here are the energy levels of those MOs. This would be the energy level diagram. Now we can put our electrons in. 2 electrons sit in this MO. That is 2 electrons are spread out in this manner across the entire molecule. Then we would put 1 electron here. Then we would put 1 here, because you fill degenerate orbitals one at a time. Isn't that Hund's rule? Then we would come back and start pairing up 5 and 6. And what do we see? All electrons paired and all electrons in bonding MOs. The same thing that we saw over here, except over here we did not have a cyclic molecule. Whenever you have a cyclic molecule, that allows for, the symmetry allows for degenerate molecular orbitals. All right. This would be the HOMO level, because there's actually 2 orbitals at the HOMO level. This would be the LUMO level. Okay, now let's do an MO energy diagram of cyclobutadiene, which has how many p orbitals, how many pi electrons? It has 4 p orbitals, and so we're going to have 6, where'd 6 come from? 4 molecular orbitals. Now the 4 will be, again, always just 1 at the bottom. Then we'll have 2. And then we'll have 1. All right. The midline runs symmetrically through here in terms of energy. Actually, in this case, your 2 degenerate orbitals fall on the midline. This is going to be an anti-bonding molecular orbital. This is going to be a bonding. Those that are on the midline are going to be non-bonding molecular orbitals. We will see why. Okay, let's try to draw these 4 first. I'll do it like this. These interact constructively all the way around. 4 atomic p orbitals interacting constructively all the way around the molecule to give 4 bonding net interactions. That is a bonding molecular orbital. 0 nodes, yeah. Okay, next we will have 2. These will have 1 node. We can do 1 node through here. If that's plus plus, that's going to be minus minus. This will be a bonding interaction. This will be a bonding interaction, constructive overlap. This will be a anti-bonding interaction, and this will be an anti-bonding interaction. And we see through here, that plane through there, there's no electron density, and that's called a node. What's the net here? 2 anti-bondings cancel 2 bondings. Uh-oh. It's 0 net. We don't have antibonding or bonding. We're going to call that a non-bonding molecular orbital. Right? Those fall on the energy midline. There's another way to have just 1 node. and that is to come through here. And there is neither bonding or anti-bonding. It's non-bonding. There's no interactions. A little weird, and I don't want to kind of get into trying to explain it because I don't know if it's necessary and I don't want to convolute it. I could possibly say some things. I'll rely on questions, but hopefully you see there's neither bonding. It's neither net bonding nor net anti-bonding. It is a non-bonding molecular orbital, has one node. Then we have one remaining, because if you start with 4p orbitals, they're going to combine in 4 different ways to make 4 MOs. This would have 2 nodes. You can draw them like this, plus, minus, plus, minus. I could have drawn that X sort of more centered in there, but I did not cut through any atom. This is an anti-bonding, 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 and anti-bonding for 4 anti-bonding net. 2 nodes. That's the worst way that these 4 original atomic p orbitals can overlap. Highest in energy. I tried to draw the 4, but in terms of the energy levels, that's what we started with. Now we can put our 4 pi electrons in. One goes here, one goes there, then one goes here, and Hund's rule tells us that the next one is going to go here. And we're done. What do we see for cyclobutadiene? The pi system, the molecular orbital description of the pi system. We see 2 unpaired electrons. Okay? It is a diradical. Radicals are fairly unstable. A diradical is very unstable. See, if we look at the structure here, okay, our valence bonding approach to structure, looks like everything's paired. But if we consider molecular orbital theory, okay, just because we draw the molecule with 2 double bonds, that doesn't mean it's actually the case. 2 paired, a bonding pair and a bonding pair, okay? This is actually wrong description of that molecule. But how else are you going to show it? You can't draw a molecule and put all this MO theory in the little structure. Not only are the 2 electrons unpaired, what type of orbital are they sitting in? A non-bonding molecular orbital. Okay? But the main thing is they're unpaired. So the difference is benzene, all the electrons are paired in bonding molecular orbitals. But with cyclobutadiene, we see that it's a diradical, 2 unpaired electrons. And that's why cyclobutadiene is so unstable. Now we have a theory that matches reality. Of course, our theory at our level right now is not overly developed. There's a lot more to it. This is just an introductory level. Okay, so we did a 6, we did a 4. What if we did an 8? Analogous to these systems. What if we did a 10? Okay. All right. They all look like cyclic conjugated systems, but okay. Well, we could do that. It's been done, and a chemist by the name of Huckel recognized a trend here, and he found that a cyclic conjugated pi system with 4n plus 2 electrons will always be aromatic. Okay? Electrons paired. Pi electrons paired in the MO. But if you have a cyclic conjugated pi system with 4n electrons, it will always be anti-aromatic. Okay? It will always be a diradical whenever you show your molecular orbital diagram. Now n here is an integer. It can be 0, 1, 2, 3, 4, 5, 6, 7, 8, whatever. Now with 4n it can't be 0 because then you would have no electrons. You've got to have some electrons. Alright. 4n, if n is 1, this is 4. If n is 2, that's 8. If n is 3, that's 12. If n is 4, it's 16. Basically, these number, okay, all right, we're talking about pi electrons, right? All right, pi electrons. And in this case, we had 4. And in this case, we had 6. Now, 6 is a 4n plus 2 number, where n is 1. If n is, by the way, if n is 0, that you could have where n is 0, that would mean 4n plus 2 is 2. If n is 1, it'd be 6. If n is 2, it would be 10. If n is 3, it would be 14, and on and on. Huckel realized that anytime you do a molecular orbital diagram of this number of pi electrons, all your electrons will end up paired. But this number of electrons, they'll always end up being shown as a diradical. So, relying on this rule, you don't always have to graph it. You can just kind of more quickly know what you're going to get if you did graph it. So, with that in mind, use Huckel's rule to predict whether this compound is aromatic, okay, or anti-aromatic. And by the way, this is anti-aromatic is when we have really a diradical. But you gotta keep in mind, this is here assuming planar. Okay? Alright? Both aromatic and anti-aromatic have to be planar because they have to be cyclic conjugated pi systems. If the system is not planar, the p orbitals are not going to be conjugated fully. If they're not conjugated fully, they're not going to combine to make these MOs. All right? And if they're not fully cyclic conjugated, then they're neither aromatic or anti-aromatic. They are thus non-aromatic. The compound is thus non-aromatic. So, give a prediction for this molecule. You can read what I wrote here about it. We'll talk about it. You can read that at the top. Okay, but also give predictions for these three. Okay, aromatic, anti-aromatic, or non-aromatic. All right. If the molecule, if the compound is non-planar, we're going to call it non-aromatic. Or this is just a particular. Basically, if it's not a cyclic conjugated system, it's non-aromatic. One way to not be a cyclic conjugated system is for it to be non-planar. Because planar on paper does not always mean it's planar in real life. All right? We'll talk about that. Predict these here. You can use Huckel's rule. Any other considerations? Then, in the next video, we will move on to MO diagrams of ions, both anions and cations. Carbanion here, carbocation here. We'll also talk about acidity of some, like these two hydrocarbons. You might think they would have similar acidity, but one of these is actually much more acidic than the other. Okay. Reaction rates, and then we'll talk about heterocycles. That is, we're going to put in a heteroatom such as nitrogen, oxygen, sulfur, maybe some other atoms, including boron. Okay. We'll ask the same type of questions that we've asked over here. Okay, guys, so please be thinking about these four molecules and then looking ahead. You also have reading in your textbook. You also have the key to drawing MO diagrams here. Okay. I think we'll end that here, and we'll finish up aromaticity and hopefully in our next video.